So lab 2 is a lab solution making lab. So solution making skill is one of the most fundamental lab skills that you have to have if you're studying molecular biology or any kind of lab-based biological science. You have to have this solution making skill, otherwise you will not be able to carry out an experiment, because your experiment will require a bunch of different solutions, so you need to know how to prepare those solutions. Okay, so having said that, then what is a solution? So solution is a mixture of solute and solvent together. Okay, solute is a chemical with a defined quantity, and it's normally dissolved in a solvent of a different kind. Most likely solvent is made out of water, unless your solute is very strongly hydrophobic. So when you mix them up together, the concentration of solute versus solvent is normally given as amount of solute per solvent. Makes sense, right? So why solutions are important in studying molecular biology? Like I said, biological molecules are very sensitive to a change of heat, pH, oxidation, or molarity. So therefore, solutions will provide a protective environment where they should be kept constant without losing their structure because of all these changes. So solution provides some protection. Okay, so you have to carry out reactions of biological molecules within a solution. Okay, because your body is full of solutions, biological solutions. You provide that by mimicking the condition. Okay, so most commonly used solvent is water, like I said. So if you said, then water, what kind of water can we use? Can we use tap water or drinking water? So the answer is no. We need to use very purified, pure water. So if you look at your course shell, there's a supplemental material you can download and take a look. So it's this. So in this supplemental material, it's a copy of some textbook that we use. There are tables that have important information. So for example, table 24.2 shows summary of specifications for various types of water. Okay, so waters can be defined into different types based on how pure those are. Okay, so when you determine their purity, type 1, type 2, type 3 are used. Normally type 1 is the purest water quality. According to who? According to College of American Pathologists. Okay, so there's an organization defining what types of waters out there based on their purity. Normally it's type 1 water that's recommended for use in the molecular biology experiment, of course. And if it's ASTM, ASTM stands for what? The American Society for Testing and Materials. Okay, that's another organization. Okay, according to their standard, there are different types, again, type 1 through 4, and then type 1 being, again, the purest. So how do you measure the purest, pure condition of the water? You can measure that using conductivity and electrical resistivity, or organic carbon content, the maximum heterotrophic bacterial count, how many bacterial cells are there, endotoxin counts. So normally it's type 1 water that you have to use for your experiment. And water quality and applications. In biological, pure water for applications such as tissue culture, life sciences, microbiology, biology, so you normally want to use type 1, okay, or 2 or 3, but yeah, type 1 is the good water. And when you make type 1 water, what water do you use? Normally feed water should have all these, maybe even the tap water, city water can be a feed water, but you will have to treat your feed city water, the tap water, through these processes like glass distillation, reverse osmosis, okay, and then all these purification methods will give you pure water that you need for your experiment. That's what it shows. Okay, so what it means is tap water is not going to be the water you are going to use in the lab. Tap water should be purified through these methods, maybe deionization or distillation or filtration like reverse osmosis or charcoal filter. You can generate the water quality that you need. Okay, autoclaving could be another way of generating pure water, because autoclaving is what? It's a steam heat treatment of water. So by doing so, you can kill any living cells exist in your water. Okay, so water quality is very important when you prepare your solution. If your solution is water-based, most common solvent used is water, like I said, and the solution making. So if you are using water as a solvent, then how do you mix with your water with the defined solute amount, right? So to understand that, we need to understand ways of expressing your solution making. Okay, so number one, how do you express the concentration between the solute and solvent? Okay, so you need to identify that amount of solute needed and amount of solvent needed. And how are you going to express that? So ratio. So there are different ways of doing that. So here are the ways. So you can basically write down the amount of weight of the solute that you need in the amount of the solvent you're going to mix together. So weight of the solute per given weight of the solvent. So weight per volume ratio. When you do that, this volume should be the total combined volume of the solute and solvent, not just the solvent volume only. Okay, so the combined volume is the volume. Okay, so if you are making maybe 2 grams of sodium chloride in maybe 100 ml of total solution, so you have to measure 2 grams of sodium chloride and dissolve it in water. And when the combined mixture, if it becomes 100 ml volume, yes, that's the weight per volume expression. Another expression is molarity. So certain amount of solute in mole amount will be dissolved in a certain volume of the water. Okay, so it could be a mole per liter normally. Oh, the unit can be changed. It could be millimole per milliliter, but you just need to be able to convert them easily. And then percent solution is another way. Percent is what? Solute amount per 100. Okay, in total. Okay, we'll talk about that. And normality. So molar and normal are similar concept, but normality is a unit you use when you describe molarity in terms of reactive acid or base. Okay, we'll talk about that. And the dilution problems. What if you have a concentrated stock solution and you need to make a dilution out of that? So how do you dilute it? Okay. So first, weight per volume solution. Like I said, given amount of solute in weight, gram, per the total volume is how you're going to make a solution. So for example, how many microgram do we need to make 100 microgram of a solution that will have 100 milligram per milliliter concentration. That's the weight, 100 milligram per every ml of the total solution. Okay, so in every 1 ml you need 100 milligram of the solute, right? But you're not making 1 ml. You're making how much? 100 microliter, which is 1/10 of a ml, because 100 or divided by 1000 is 1 ml. 1 microliter. So if you convert milliliter to microliter, so 100 over 1000. Okay, so in 1 milliliter, which is 1000 microliter, you need 100 milligram. And how much of that solute you need? If you're making 100 microliter, which is 1/10, so 1/10 of that is what? 10 milligram. It's straightforward, right? And about molar solution. A mole in chemistry is defined as what? 6.02 times 10 to the 23 number of atoms exist. That's the amount of mole, right? So weight of 1 mole element, we call that as atomic weight or molecular weight or formula weight. If you look at the chemical equation that's describing the particular chemical, you add up all the atomic weight of all those elements together, then it'll give you the molecular weight, right? So how do you make, for example, 0.2 molar sodium hydroxide? So sodium hydroxide, if you look at their atomic number, so atomic weight, okay, you will realize it's 40 grams. So if you do not remember, you can just look up the chemical bottle. Normally, chemical bottle of sodium hydroxide says what its molecular weight or formula weight is. It's 40 grams, it'll say it. Okay, so 1 mole of sodium hydroxide will be 40 grams of sodium hydroxide in 1 liter of total solution, right? That's 1 mole. But you are making only 0.2 molar. Okay, so then you have to consider it's 0.2 over 1. Okay, so 0.2 divided by 1, right? So how much is needed then? If you're making 1 liter, it's that, but now you're making only 500 milliliter. Okay, so I guess this is the question. So 0.2, so times molecular weight 40, okay, times, let's say you're making 1 liter, times 1 liter, and it'll give you the needed amount of sodium hydroxide. That's how you're going to calculate it. So basically you're multiplying everything. Concentration times molecular weight times 1 liter volume is going to give you the defined amount of the chemical unit. How about this question? How much of sodium chloride is needed to make 500 ml of 2.5 molar sodium chloride? Okay, again, sodium chloride NaCl molecular weight is 58.44 gram per every 1 liter. Okay, now you're making 2.5 molar, so 2.5 mole times molecular weight is what? 58.44 gram. Okay, times how much? 500 ml, not 1 liter. So it's 500 over 1000. Okay, is the volume you're making. So if you multiply them all, you can find out how much that is. Okay. How about normal solution? I told you the number of mole equivalent per liter of solution, that's what normal is, especially in terms of reactive chemicals like acid, strong acid. Then you are using a normal concentration instead of molar. So mole equivalent weight is the number of gram of a reactive chemical to yield 1 mole. That's like H plus or H minuses. So to understand the normal ratio, you have to look at the chemical equation and determine the number of hydrogen ions or hydroxy ions per mole. Okay, how much of them are made. So if you are looking at NaOH, it's 1-to-1 ratio. Okay, but if you look at H2SO4, okay, then it's going to be so 2. Every 1 mole you can make 2 normal. So the ratio will be different based on the equation. Okay, but the way to calculate the same: concentration times molecular weight times the volume. That will give you the amount of the chemical unit. And then percent solution. Percent is weight of solute per 100 ml final volume, final solution. Okay, it could be given as a weight per final solution volume, or it could be volume of solute per 100 final ml volume, or it could be a weight of solute per 100 gram of final solution. Okay, but whatever that is, and it's always in 100 of total. Okay, so example is, how would you make 500 ml of 5% solution? 5% is what? 5 over 100. So 5%, so change that 5 over 100 and you multiply that to 500. Then you can figure it out how much you need. Okay. And what if you are preparing a dilution from a concentrated stock solution? How do you do that? In that case, you use this equation. Okay, Ci times Vi equals Cf times Vf. In this case, C is the concentration, V is the volume, and I is the initial, and F is the final. Okay, so initial concentration times initial volume equals final concentration times final volume of your solution. Okay, so example, what does that mean? How do you prepare 1 liter of 0.2 molar solution of sodium hydroxide from 1 molar stock solution? Okay, so in this case, the final volume is 1 liter, and the final solution is 0.2 molar, right? So 1 liter times 0.2 molar equals, what's the initial concentration? 1 molar. 1 mole times unknown volume of that, so 1 mole times X, unknown. And you solve the equation for that unknown volume, then you can figure it out. Okay, that's how you do it. Same way with this. If it's a percent, same way. 0.2% STS times final volume, 200 ml, equals 0.4% times unknown volume of that. So solve the equation for unknown volume. Then you figure out how much of the stock solution you need. Okay.